We're going to talk now about what is the relationship, if any, between, say, nucleophilicity, and basicity. So, nucleophiles and bases. We know that nucleophiles and bases are electron-rich species. What makes them different? We know that when we have a base, it will attack on a proton. So that is a proton transfer reaction. And the same species could be acting also as a nucleophile, but I'm here going to just write nucleophile. It is attacking on a different atom. Typically, it could be a carbon atom, for example. But it could be boron, it could be something else. But essentially, this needs to be electron deficient somehow to be likely to be attacked by a nucleophile. And here, this is a hydrogen that is acidic, meaning attached to something, say electron withdrawing. But essentially, these are acid-base reaction in the Bronsted-Lowry concept. And this will be attack on an electron deficient species. You can see that as a Lewis acid-base reaction. My point is, there are some molecules that can act both strong bases and strong nucleophiles. For example, if we have etoxide, and say that we have, I'm going to draw here acetic acid. And so you can have, this is your base, electron rich, and it's going to attack on the acidic hydrogen, the product. So when you will have the other arrow, that's your acid here, and you're going to create the conjugate acid, ethanol plus acetate, your conjugate base. Here, conjugate acid, conjugate base. Okay, that's a proton transfer reaction. Now, ethanol, we know it's a strong base because it's conjugate acid. It's a weak acid. The pKa of ethanol is about 16 units. And to just have that, those numbers, say in perspective, remember that sulfuric acid, pKa is -9. Hydrochloric acid, another strong acid, the pKa is -7. So the smaller the pKa number, the stronger the acid. So this is fairly weak acid, so strong base. But also, etoxide could be acting as a nucleophile. This time, if it is attacking on something else. For example, this triethyl bromide here. And the carbon here is electron deficient. It is electrophilic. Remember, this bond is polarized towards the bromine. So what happens here is now etoxide this time is attacking on a carbon atom. So here is acting, etoxide acting as a base, etoxide acting as a nucleophile. Again, we cannot break the octet rule, so I must draw a second arrow. And here, the product, I need to draw it lower, right? The product is going to be diethyl ether. And plus, here you have the parted bromide is your leaving group. So you're forming that. So that's your reaction. What we see here is a species that can act in two capacities, as base or as nucleophile. It turns out that etoxide is a strong base and also a strong nucleophile. Knowing that is important when we're going to decide, for example, what would be major product, what is going to happen in a particular reaction. And it's critical, for example, when you're predicting products in SN2 versus E2 products, which we see later. So substitution and elimination. So understanding that difference is important. So we have other species that can be both strong base and strong nucleophile. And examples of that, let's see, I'm gonna erase that here. So examples, so where there is a parallel, a strong base is being a strong nucleophile as well. So for some species that works. in strong bases. BuOK is strong nucleophile, for example, in the case of butoxide. And again, we said coming from a weak acid, ethanol, pKa 16. We have also methoxide, similar, is coming from the conjugate acid is methanol, similar pKa. We also have hydroxide. Hydroxide is the conjugate base of water. pKa is 15.7. So all of these are strong bases and also strong nucleophile. And now we're going to see other examples of that behave somewhat different. Let's think now, say that I have a reaction in which I want to use, say that I want to use Tert-butoxide in a reaction. Typically, we see this reagent written as potassium Tert-butoxide. We know this is positive, that's negative, so that is my molecule. Now, if we look at the pKa's of a conjugate acid, and that's tert-butanol, right? So adding an H here. pKa here is 18, so very weak acid. That makes tert-butanol a strong base. However, it's a weak nucleophile. It's not as good because it's not the same to attack on a proton. Let's say that it's doing this. It's not the same as attacking on a carbon like that. So let's change the nucleophile here, and I am going to add 2 more carbon chains. Now it is tert-butoxide. Now this, remember, our metal group. This is pretty crowded, so it makes it big. The fact that it's big, that is a lot of steric hindrance to approach here the alpha carbon. Because of that, tert-butoxide is weak nucleophile. So we classify that as tert-butoxide as being a strong base. It's still a strong base, and we know that because comes from this weak acid, tert-butanol, right? It's conjugate acid. It's very weak, so strong base. But due to the size and the steric hindrance, it is a weak nucleophile. So not always strong bases are strong nucleophile. In this case, it's weak. So we have more examples of, bases that are actually not good nucleophiles if they have also a lot of steric hindrance. So I'm going to keep my tert-butoxide here and just going to draw a couple more examples in which not necessarily basicity goes along with nucleophilicity. So another example is the isopropyl amide. So this is the isopropyl group. This, remember, is a metal, another metal, so this is quite bulky. So it's a very strong base, but not a good nucleophile. Or even that, if you have it like isopropyl amine, so the amide is with a negative charge, but if you have that, still you have the lone pair here, but not as good a nucleophile because all of this bulky thing. Remember that to act as a nucleophile, it must attack on a carbon, and that's pretty crowded here to get. So it's not going to happen. It's not nucleophilic. Another example is, we say triethyl amine. Triethyl amine is, remember, ammonia. If ammonia is this, right? Think of replacing each of the hydrogens by an ethyl group. So it looks like this. So again, pretty bulky here. So it can act as a base, but not as a nucleophile. So again, conclusion here is that some species can act as a strong base, strong nucleophiles, the ones that I have here. But when there is a lot of steric hindrance, there's a lot of size, bulky, then they rather be bases. They are strong bases, but not good nucleophiles.